All right, we're going to be talking about some exponential expressions and how to solve them when we can make the bases match. So as you can see here, I've got a fraction of a worksheet here that I would like to discuss. I'm going to start with some of the easier questions. So I'm going to start here with number 14. Number 14 is very easy because what we're going to notice is that the bases match. So equals means is the same as. So if we get the same thing on the bottom of our exponent, it stands to reason that we're going to have the same thing on the top. So in the case of 14, we're just going to say 2k equals 2 and call it a day. Well, we're also going to divide by 2 to get k equals 1. And that's going to be the entirety of how we deal with 14. We're done. That's it. So if we look at 16, also base 4 on both sides. So if we say the 4 to the stuff equals 4 to the stuffs have to match. Therefore, negative 3n equals 2n. This is only going to be true when n equals 0. If you prefer, you can add 3n to both sides and get 0 equals 5n and then divide by 5. But either way, n equals 0 is going to be the only solution for 16. Now, for the rest of these, we may have to be, well, okay, 19 is pretty easy too. 19 again, the bases match, so 2k minus 3 equals 5. And we can solve from there, 2k equals 8, k equals 4. Bada bing, bada boom, these are nice and easy. Now, just about all of these other ones are going to be a little more complicated. The only one that doesn't follow the same mold as the others at this point is 12. And 12 really kind of looks like the questions we just did a second ago, and it is, in effect, because it's 3n equals 3n. But this one's a little weird. You have to ask yourself, when does 3n equal 3n? Like, is there a specific number? Like in these ones, k equals 1 was the time that made 14 true. N equals 0 is the time that made 16 true. When does 3n equal 3n? Doesn't 3n always match 3n? Does it matter what value you pick for n? Like if we just divided this by n, wouldn't we get 3 equals 3? And 3 always equals 3, right? Doesn't matter what n you pick. So this is just always true. So the answer to this is all real numbers. Or you can draw that fancy scripty R thing with the extra downward line if you prefer. But it's everything. Okay, well, that's great. Now let's talk about these other ones. Now, the deal was, in order to use this rule, we had to have, like we had a to the stuff equals a to the stuff. Or let me use a different symbol here. And then what we concluded then was that square equals triangle. We're going PlayStation controller on you today, apparently. The problem with these other questions is now it's a to the stuff equals b to the other stuff. And you can no longer say this is true. The reason why this first statement works, the reason why that is true, is because what we are effectively doing is we're taking our original statement here and we're doing log base a on both sides. If you do log base a of a to the something, it just equals the something. So in effect, we are canceling the log a with the a to the and the log a with the a to the over here, and we end up with square equals triangle, whatever those things happen to be. Well, that doesn't work over here because we do log base a, pretend that says log, and we do log a over here. Log base a of b to the, we can't do anything with that. I mean, technically, I guess we can use a log property and bring this exponent out front, but that's not really what we're aiming for. What we really want to do is make it so that we can do a log on both sides and it just cancels. And we can't do that until the bases match. Well, the good news is every single one of these questions is rigged so that we can make them match. Either they are like number 15, where we have two exponentials that have very different bases, but we can make them match, or they're like 11 or 13, where the one side isn't actually an exponential, but we can write it as one. And whatever base we use, we can make them match at that point. So I'm going to hold off on 11 and 13. Let's start with number 20, actually. I think 20 will be the easiest place to start here. So it writes 2 to the fourth here. Now you could turn that into 16, but actually 2 to the fourth is the way we want this written. So we're going to leave this as 2 to the fourth. The reason why is because this number 32, we can write as a power of 2. Think about your powers of 2. 2, 4, 8, 16, 32. So this is 1, 2, 3, 4. That's 2 to the fifth. So what I'm going to do, I'm going to write 2 to the fifth to the negative 3x. And now we're going to use our exponent properties. Power to a power means we multiply. So this is 2 to the negative 15x is equal to 2 to the fourth. Okay, true or false? This now looks like the problems we did before because now the bases match. So now our square equals our triangle, and negative 15x equals 4. So x is equal to negative 4 over 15. And we're done. Oh, is that simple, huh? Sure, simple, he says. No, I don't pretend that these are straightforward, but every single one of these questions is designed to work that way. So let's look at 18. We've got 6 as a base over here. We got this number 216. What can we do with 216? Well, let's start looking at powers of 6. 6 times 6 is 36. What's 36 times 6? Well, it's 180 plus 36. That's 216. Oh, hey, there we go. So this is basically 1 over 6 to the third, or if, in other words, it's equal to 6 to the negative third. Remember how negative exponents work. So now, if we focus in on this and we say 6 to the 3 minus 3x equals 6 to the third, now we can say that our bases match and we can set them equal. We go 3 minus 3k is equal to negative 3. So negative 3k is equal to negative 6. And so k is equal to 2. Okay, so those are the two easier ones where the bases match, or maybe 11 and 13 are okay in that regard. 15 and 17 are going to be a little trickier. So let's hammer out 11 here. 36 and 1/6. What's the base number we want to use here? 1/6. Well, like 1 over 216, I think we're going to need to deal with negative exponent territory here, but 1/6 is not nice to write that way. We're going to have to write as like 6 to the negative 1, I think, because we need an exponent of some kind to do this particular process. Okay, so 36, well, 36 is a power of 6, isn't it? Let's go with that. Let's roll with that. So 36 is 6 squared. So 6 squared, aka 36, to the 3x. And so now we'll use our power to a power. We'll say 6 to the 6x is equal to 6 to the negative 1. And now we can make square equal triangle. And so x is equal to negative 1/6. The same thing is going to happen for 13, except it's a lot closer to what 18 did, where we have a number over here, and we're going to write this in terms of that number. So powers of 3, let's think. We've got 3 times 3 is 9, times 3 is 27, times 3 is 81, times 3 is, let's pray, 80 times 3 is 240, 1 times 3 is 3, add them together, we get 243. All right, so this right here is 1 over 3 to the fifth, or in other words, 3 to the negative fifth. So now square equals triangle. Negative 3n plus 3 equals negative 5, and from there you can solve it and do all your usual Algebra 1 stuff that shouldn't hopefully be too hard at this point. Now, 15, 17 use 64 and 16, both of them do. The way we've done this up until now is we've said, okay, we make them out of the same base. And we went, oh, well, 216 is a power of 6, 32 is a power of 2, 243 is a power of 3. It's been nice and easy like that. We just say, oh, the bigger number is a power of the smaller number. But 16 squared is way more than 64. It's 256. So what? What do we do? Well, it turns out if we can write one of these numbers as a power, turn it into an exponent, maybe we can do it to both. Are 64 and 16 both powers of something? Well, 16 is 4 squared, right? 4 times 4 is 16. What's 16 times 4? Ka-ching! There we go. So we're going to say that 64 is 4 to the third to the negative 2r minus 1. And 16 is 4 to the second to the negative 3r. And now we're going to use power to a power. We're going to say 4 to the negative 6r minus 3 is equal to 4 to the negative 6r. Oh, this is interesting. Okay, so we're going to reduce this. We're going to get negative 6r minus 3 equals negative 6r. Let's add 6r to both sides. We get negative 3 equals 0. When does negative 3 equal 0? Think back to what we were talking about when we said number 12, when 3 equals 3, that's just always true. When does negative 3 equal 0? Can you give me a number that we could plug in for our variables r, plug in for r, that would make that true? I can't think of one, can you? Negative 3 is never equal to 0. This is just never true. The answer to number 15 is no solution. It ain't gonna happen. Nuh-uh, ain't gonna do it. All right, so that's 15. 17, I'm gonna come down here to this blank space in this area for 17. So 17 is gonna be the exact same setup. We're gonna say 4 to the third to the 2x minus 3 is equal to 16 is 4 to the second. So 4 to the power to a power, 6x minus 9 is equal to 4 squared. So 6x minus 9 is equal to 2. That's the square equals triangle thing. And now we'll add 9 to both sides, and we'll divide, and x equals 11 over 6. So unlike number 15, which was no solution, this one had a legit answer. So this is going to be your general theme for how you're going to process these. And it's pretty much as straightforward as that. Now, I do want to point out that when you're doing this kind of question, since it is entirely possible that your teacher is going to throw these at you a whole bunch of times in a row, like across several worksheets. So what I want you to think about now here is some of our powers that we may want to recognize. So powers of 2. Go 2, 4, 8, 16, 32, 64, 128, 256, 512, and I don't think we need to go past that. Teachers like to do powers of 2, so I wanted to throw in a bunch of powers of 2. And of course, we can count these. We can go 1, 2, 3, 4, 5, 6, 7, 8, 9. The 10th one is 1024. Every once in a while, they'll dust that out. That's important for computer programmers, but probably not so much for Algebra 2 students. Powers of 3. Go 3, 9, 27, 81, 243, and after that, it gets a little too big to be reasonable. The next one's 729. So again, these are, other than maybe that last one, numbers that you should be on the lookout for because they're going to show up in your practice problems. The teacher is going to write questions that are rigged to use these. Powers of 4 are going to go 4, 16, 64, 256, and then get too big. It's worth noting that these are all powers of 2. In fact, they're literally skipping every other line in the powers of 2 list. So you don't have to use powers of 4 ever. You can just use powers of 2 instead if you choose to. But we're going to at least list that. And then powers of 5. Go 5, 25, 125, 625. And after that, I don't think it's reasonable to know them. So 1, 2, 3, 4. Those are the powers involved. Um, and then let's just rattle off a list of some others. So 6 goes to 36 and then 16. 7 goes to 49, and probably you don't need to go past that, but the next one is, I think, 343. 8 goes to 64, and then you probably don't have to cube it. 9 goes to 81, and again, you probably don't have to cube that either, but I'll write these in just in case. And then you definitely want to know your powers of 10, because they are super easy. You just keep adding zeros. There's nothing to them. So you're just going to keep going with that. And then we want to talk about squares. 11, 121, 12, 144, 13 is 169, 14 is 196, 15 is 225. You probably don't need to know your squares past 15, but these are numbers that I expect you to possibly see in this style of question. So if you see any of the numbers on this chart here, you should recognize that you should cut to whatever power they represent, such as if you see a 512, you can write that as 8 to the third. If you see a 49, that's 7 squared. If you see a 125, that's 5 to the third. If you see a 128, you can treat that as 2 to the seventh, etc. And that way, you can probably answer all of your square equals triangle questions. Um, Also remember that if you see something that's on the bottom of a fraction, that just means that the exponent, the power, is going to be negative. And other than that, you do it the exact same way. So these are things to consider when you're doing this kind of question, and hopefully that will get you home.